calculating VO2, what we're looking at is the air inspired and the air expired. Now in lab conditions, the air inspired is the lab air. It goes through one side of the mouthpiece, and the air expired goes through the tubing and it's captured in a Douglas bag, which we analyse later on. So we analyse this expired air and we look at its composition and we compare it to the air that we inspired. Now the oxygen that's in the air that we inspired but doesn't come out is consumed by the body. It's our VO2. Likewise, the carbon dioxide that comes out but we didn't inspire, it's produced by the body, and that's our VCO2. So in order to calculate VO2, we need to measure some things. We need to measure the volume expired, which we do by vacuuming the air out of the Douglas bag. We need to know the fractions or percentages of expired O2 and CO2, which we figure out by using the analysis of 30 seconds or a minute of the sample. We need to know the temperature of the expired gas, which we figure out at the same time when we do the volume. We also need to know the barometric pressure inside the lab. We also need to know a few things. We need to know the volume of inspired air, which we didn't measure, so we need to calculate it somehow. We also need to know the percentage or fractions of inspired oxygen, carbon dioxide and nitrogen. Now these values are standard values, so they're already known. We know what these are. And we also need to know that the body will neither produce nor consume nitrogen. So what goes in will always come out. So here's some example data from an elite cyclist cycling at 100 watts. Now this is the exact sort of data you would have been collecting in your prac classes so far. So let's use this data and work through an example, sample metabolic equation 1 in your handout. So step 1, before we calculate anything, we need to convert the volume of gas that we collected in lab conditions. We need to convert this to standard conditions. So not just what it happens to be on the day, but to a standard temperature, which is 0 degrees Celsius or 273 degrees Kelvin, a standard pressure, which is 760 millimeters of mercury, and dry, so no humidity, no water vapor in the sample. We're going to take what we collected and convert it into these conditions. It's going from ATPS, ambient temperature pressure saturated, into STPD, standard temperature and pressure dry. So we're figuring out what this volume would be under these standard conditions, knowing that temperature and pressure will both affect volume, and so will the water vapor content in there. So we take Boyle's law and Charles's law, we rearrange them a bit, and we get an equation that looks like this. What we're doing in this equation is we're taking into account the water vapor pressure, so mathematically we're drying out this sample, and we're also converting our expired air temperature in Celsius to degrees Kelvin by adding 273 to that number. So if we enter in our data, your equation should look something like this. Here's our collected data of expired air temperature, our barometric pressure and our volume expired. And this is our pH2O, or our pressure of water vapor, and we figure this out using a table corresponding with our expired air temperature. We enter this data in, you should get a number around about 33.66 or 33.67 litres of expired air standard. Step 2, we calculate the inspired air volume. So we didn't measure this, we've got to calculate it. And this is where our knowledge of nitrogen comes into it. So we know air is always 0.7904 nitrogen. And we know that none of this nitrogen is going to be consumed or produced by the body. So we also need to figure out what our fraction of expired nitrogen is. So what we do is we start with 1, and we take away our collected fraction of oxygen, carbon dioxide, enter that into the equation, and that'll give us our fraction of expired nitrogen. We enter that value along with our known value of nitrogen into this equation, and we multiply that by our calculated VE that we calculated in step 1, and we should get a volume inspired at 33.76 litres. So step 3 is calculating O2 consumption, or oxygen consumption. Now step 1 and 2 was just giving us all the information we needed to get to step 3. And what we're really doing here is we're taking the volume we inspired and we're subtracting the volume we expired of oxygen. And that's the volume of oxygen that stays inside the body during that minute. That's our O2 consumption. If we enter the data in like such, using our collected data there, our known value of air, 0.2093, our calculated VE in step 1, the VI we calculated in step 2, and that should give us an answer of 1.61 litres per minute. That's our VO2, or our oxygen consumption. Step 4 is much like step 3, except this time we're using fractions of carbon dioxide and we're taking away the amount we inspired from what we expired, because we always expire more CO2 than we inspire. Enter our data in like such, our collected CO2, our known value of air, 0.03% carbon dioxide, our VE we calculated in step 1, and our volume inspired that we calculated in step 2, and you should get a VCO2 of 1.52. 1.52 litres of CO2 were produced in that minute. So let's look at another example using your own prac data from prac 2 and prac 3 of one of the students exercising on the bike at 100 watts. This is the same data you have collected in your prac classes. So let's work through steps 1 through steps 4 and see if your answers are somewhere close to the mark. So step 1, entering your data into this equation, should look something like this, and you should get a result somewhere in the ballpark of this figure here. 29.039 litres volume expired. Our inspired volume, we enter the data into the equation to figure out our fraction of expired nitrogen. We enter that along with our known value of nitrogen of inspired air into the equation and our VE, and we come up with a volume inspired somewhere around this figure, 29.27 or 29.28 litres inspired. So we enter the data from step 1 and 2 and our collected data into the equation in step 3, calculating oxygen consumption. Your equation should look something like this, and you should get a result of about 1.62 litres per minute, VO2. Step 4, much the same, entering your data in, your equation should look like this, and you should get a result of 1.38 litres VCO2, or CO2 production. Sample equation 3 in your handout is using data from a type 2 diabetes patient, also cycling at 100 watts. So using this data, work through your equations, step 1 through step 4, and see what result you get. You should get a VO2 and a VCO2 around these figures here. So let's compare our VO2s. You should have calculated that for your elite cyclist, EXSS student and a type 2 diabetes patient, all at 100 watts were consuming 1.6 litres per minute. So power output is the same for the same VO2 for everyone regardless. But when we look at heart rates, we can see the heart rate for the cyclist is lower than the student, which is also lower than the type 2 diabetes patient. So this alludes to the concept of capacity, which Nathan is going to deal with in future lectures with you. Up on WebCT, along with this presentation and your handouts, is also an Excel spreadsheet which will calculate VO2 and VCO2 for you using the raw data when you enter it in. But it also has tabs behind there where you can look and see the equations and the explanations for the equations, step 1 through step 4. So use this to check your answers, but don't rely on this completely, because in your end of semester exam you're going to have to calculate VO2 from raw data using these equations.